Alright, here we have a small fatigue problem. So we've got a spring which is fluctuating between 60 pounds and 150 pounds, and through that fluctuation it deflects by 1 inch. We want a specified life of 10 years of 1 shift per day operation, and we're just designing a spring to fit the situation with a material provided. The 1,000 RPMs there, it's not an assumption, it's necessary to solve the problem. We've got to know what speed the spring is being cycled at in order to calculate the life. Plane and ground, that would be an assumption. And setting NF equal to 1.5, you could call that an assumption as well. And do bear in mind, as we're going through this problem, requiring a factor of safety based on fatigue, we still have to check against yield just like any fatigue problem. And it's entirely possible that we're going to end up with a spring that just to get a spring that won't yield, we're going to end up with a higher factor of safety against fatigue. And in fact, in this problem, that's exactly what happens. Now, the music wire in this case is shot peened, and we're going to start with a wire size of .207 inches to begin the problem. I've worked a lot of this out just to save a little time, as this is kind of a long problem start to finish. But to begin with, we're dealing with that shift. 10 years at 1 shift hour per shift, I think it was. So if there's 8 hours in a shift, 5 days per week, 52 weeks a year, we get about 2,080 hours out of that. And then converting the 1,000 RPMs, I guess I'm looking at this as some sort of, say, camshaft, which is depressing the spring as a follower, something of that nature. So I'm saying the spring gets cycled 1,000 times per minute as well. Convert to hours, convert to years, multiply by 10 years. And we actually see that this is going to needs to run for 1.2 e to the 9th cycles. Now keeping in mind that the endurance limit for steels is set somewhere between 1 e to the 6th and e to the 7th, we're definitely in an infinite life sort of case here. So we'll base all this on the endurance limit. Now the next thing done is just to handle the forces, calculating the alternating and the mean force, which I can then use to calculate stresses. In this process, you actually only need the alternating force, but you might as well do them both. And you could calculate stresses from the max and min force and then calculate other things, but to me it's just easier to deal with the forces up front. The stiffness coefficient, that 90 pounds, is moving from 60 pounds to 150 pounds. That's a change of 90 over a change in length of 1 inch. We get 90 pounds per inch for the spring constant here. The strength for this material, which is the music wire, we've got A is 201,000, the exponent M is .145. That gives us our ultimate strength. From the table lookups with this material, in an unset condition, we got 45% of the ultimate strength as yield. And from the signed Zimmerly data with a shot peen material, the alternating strength in fatigue is 57,750, and that's PSI as well. Now to begin the design process here, this actually fits reasonably well through the design tables. If you want to go about it that way, you could go back and just calculate these things directly based on shear strength, factor of safety equation, and a stiffness equation. But it was a reasonable match to the table, and specifically I want to kind of show some changes that you can make to that flowchart in order to solve fatigue problems. And there's just 3 replacements you make in the process. In the table, in calculating alpha, you have SSY over NS. That's producing a spring which will yield right up to its solid shut length. But we're wanting a spring that works in fatigue, which means we're probably never going to approach the shut length. We need to base the factor of safety here off of fatigue factor of safety first off, and then that that alternating shear strength. So by making those 2 substitutions, we're basing strength entirely on the fatigue properties, both the factor of safety and the strength of the material. The second replacement to make is anywhere you have what was F max in the flowchart, you can replace with FA, which is the alternating force. Remember, the signed Zimmerly assumption basically says that the mean stresses, and as such the mean forces, have little impact on the overall fatigue life. Now in the table, that's often, you'll see it as 1 plus xi times F max, where Xi is the fractional overrun, and that again, that's related to producing the spring which operates safely at its shut length. But since we're not working specifically towards a shut length, I'm not including the fractional overrun in this case. Just the pure FA, which was 45 pounds. So solving for alpha and beta and then C, we get 13.69, which is actually a little bit outside the range that is specified for a reasonable spring design. I think 12 is the maximum that's mentioned. So that initial wire size of .207 was not a great choice for this problem. Now to continue the problem and see what we actually need to do to the design to make it worthwhile, I'm going to switch over to Excel and take the same numbers from here and do some manipulation and see what we can come up with. Alright, so here we are in Excel. We're starting again with the .207 diameter. We got material properties which match the previous pages, and in FA I'm calculating alpha and beta, and there I get the same C value as we had from before as well. Now if I look down here where I'm calculating the alternating stress and factor of safety, I get 1.5 since this design is based off requiring that size, and I actually get a yield factor of safety less than 1. So this spring is going to fail at these operating loads. It's outside the practical limit based on C, and it's also just not going to work. It's not strong enough as it is. Coming down here, let's take a look at the number of active coils, .896. So not even a full coil diameter to get the stiffness required. So that's not in any way a practical spring geometry, and as stated here, it is going to fail. So looking at some possible wire sizes, which is in the browser over here, we're at 207. I know I'm going to want to go to a smaller wire in order to possibly have anything. I'm just going to go to the limit of this chart, which is .125. You can definitely get wires smaller, but let's just see what happens. It's still yielding. We now have about 25 coils, which is too many. This is just not going to be a practical design as it is. That is shooting for a fatigue factor of safety of 1.5. We're going to end up having to redesign this based on yield and then check the fatigue factor of safety, because as it is, we just can't get what we want having NA, that should be NF actually, having NF be 1.5. So what I need to do is redesign the spring to have a reasonable yield factor of safety. I'm going to take it as 1.2. Now this is not a shut NS factor of safety because we're not designing the spring to operate over its full travel. So that's why I'm calling it NY. So all I need to do in order to make these changes is reset my design equations to be based on the yield strength and a yield factor of safety. And just to make that clear, I'm going to go ahead and replace this with 1.2. And then in alpha and beta here, see right now it's based on the shear strength alternating. I'm going to just drag that up to be based on Y. And same thing in beta, where I'm based on the alternating load here, I'm going to base it on the maximum force. So now I'm designing the spring to be based on the fatigue factor of safety. And I've got one little typo here. I was including the fractional overrun in this original problem. I'm just going to get rid of that. And now we've got a spring with a factor of safety of 1.2. And then coming down here, the fatigue factor of safety now is above 1.5, but that's okay. There's no problem with that at all. So this, strength-wise, is a reasonable spring, but looking at the number of active coils, we're approaching 100 now, which is in no way practical at all. So we need to bump the wire size back up. Let's try .207 again. So for this stiffness requirement at .207, we've got our yield factor of safety. Our fatigue factor of safety is now well above the limit. We've got 2.516 active coils, which is not that great, and somewhere in the 4 to 5 range. I think the chart may say 3 and up, but let's try to get that a little bit higher by going to a slightly smaller wire. Let's try the next size down, .192. Now we got 3.8 active coils. That's not bad. I'm just going to drop one more, 1.875. This isn't going to make much of a difference, but There we go, 4.377 active coils, 5.377 total. We got the free length, the shut length. All these things are now good to go. The last thing I'll say about this design is I've mentioned a couple of times that we're not specifically trying to drive it to a shut length. And this assumption right here, where we take the shut length and add the maximum displacement to get the free length, that can be bigger than that. That's not required to be just the shut length plus the maximum displacement. I can add in just about whatever I want into that as long as I'm not making the spring unstable. So I could have this be just 3 inches. It's the same number of coils, they're just stretched out a little bit more. But stretching those coils out doesn't affect the strength and it doesn't affect the stiffness. So if I need a spring whose free length is a little bit longer or shorter, I can adjust that as needed as long as I'm checking that I'm not exceeding the critical buckling length, which I don't have this sheet to set up to do, but that's something that could be added back in.